Alright, hello everyone, welcome to another stream. How are we doing? So, apologies, I'm not very set up at the moment. Let me just post that I'm live and bring my standing desk down to being a regular desk. Just bear with me for one moment. I had to get my son ready and I was just, one of them. So last stream we did hot code reloading to the engine, which was proper cool. Just make sure that was all coming through okay. Good. So we had a hot code reloading for shaders, not for CPU code, just shaders. And we added support for multiple shader binaries to be loaded. So we've only got one SPIV file right now, but we added support. See here, it's this SPIV file here. And we added support for multiple because our materials are going to be procedurally generated at build time, and they're going to use shaders to do that. So you'll be able to make a custom shader. You'll be able to make a nice custom shader to launch, and it will generate a bunch of different materials using the same shader with different parameters, and you'll be able to use that at build time to obviously pack a bunch of PBR shaders, which is proper cool. This is the aim and objective. So essentially we're building our own type of kind of like substance designer system, similar to that but without all the node graph crap, just it's all with code, right? And it's only for ellipsoids and things. Okay. And what else are we doing? So today we're working on the renderer, which is always good and fun. Here's this plan that we've been making off stream. Sorry, we're making on stream and off stream. So I made some changes off stream. Hey there, Akraz, welcome, sir. And welcome, Dehamet. Welcome. And standing desks, do you feel better using it? Well, I don't feel better when standing. It makes my knees hurt. So what I have is, hang on a minute. Let's get the infinite treadmill going. I was one of these. Have a treadmill. So what I do is when I basically walk, right, instead of standing, and then it sorts my knees out. So my knees, I used to play a lot of like football, not very good at it, but I used to play it, and I kind of wore my knees out a bit. I don't know. I have some kind of condition where my joints aren't really the best, so my knees feel proper worn out. So I can't really stand for too long still. I have to always be kind of slightly moving. So the walking desk helps me sort of think and not have to think about keep moving, because I'll just be walking, you know what I mean? Because the problem is when I'm sort of standing up during the day, as soon as I start thinking, my mind's like, oh yeah, I just stand still all of a sudden, and then I end up sort of getting to a very weird posture while standing, and it's very hard to keep being aware of correcting that. So the treadmill really helps me just sort of, my mind is just knows I'm walking, so I can just think about other things or just work, and it's really good. I love it. So I actually walk for I do about 700 calories. That's what it says. So I walk for maybe 4 hours a day, maybe more. About 4 miles an hour. Right. The desk is nearly sorted out. For me, walking and standing would be bad. I have no problem with riding though. Yeah, you can go riding desk. All the way. The riding desk. Beautiful. You should do it. So, because my standing desk is not tall enough for me when I'm on the treadmill, I've also got a little wooden table. So it's just put my keyboard on it and mouse. It's actually really good. Helps out a lot. So I'm super happy about that. It's really sorting out tons of stuff that's wrong, like my wrists and my my neck and everything is just all feels really good when I'm just standing and walking and stuff. So I'm happy about that. But obviously while I'm streaming, I sit down because if not, I'll just be making treadmill noises, which won't really be ideal. Hey, Perry. Ugh. Right, time to bust down another Coke. I've not been getting the best sleep at the moment, so Coca-Cola it is. I need to come off this stuff again. I'm kind of mid. I'm dependent on it at the moment. This is not good. It needs to come off. There's too many DRUGs in life. Substances that people do that are illegal. Why are these things sold? And I got a tea, a nice ginger tea, just to sort of counteract the gut issues you get from drinking too much Coke. There you go. It tastes really good. I do like it. It also just, I've not been getting good sleep at the moment. It's got caffeine in it. It tastes good. So it helps me. I'm kind of got myself in a stupid rut at the moment where I'm kind of probably would need one right now. Otherwise, but yeah, I should come off it fully because you don't need Coke. But I've just not been getting good sleep lately for reasons. But yes, like in the most optimal state, you do not need any caffeine at all. You can just, have basically low sugar. Just avoid all sort of like sugary snacks. Avoid all caffeine, and kind of try and get some ideal amount of sleep. And you should typically not need any caffeine. The problem is when you have a little bit of caffeine after a while, then you're like, this stuff helps so much. And then you trick yourself into start having more and more and more. And then you're just back in the rut again. So that's the problem with all this stuff. It's such a trick, man. Black tea, you like a black tea, right? Yeah, well, do you have any sugar in that as well? So last stream we said we was going to work on like a texture cache, whereas going to have like support for all sorts of textures and stuff. Fix allocate a bunch of like texture 2D arrays, right? So a texture 2D array is like, imagine if you have like a texture, but there's a bunch of layers to it, right? So layer 0, layer 1. So you can try kind of think of it as like a 3D texture in a sense, right? But it's got like a bunch of layers that go behind it, yeah? And so if you pre-allocate one texture 2D array with like 1024 slices or layers as we call them here, you basically can have like 1,000 textures in one texture basically. And so I was thinking about having this sort of like texture cache system for like materials and thumbnails and stuff, but then I was like, you know what, let's just focus on it being a material cache and just put it all in this system. So this is what we're going to build today, is a way to essentially have our to avoid dynamic allocations at runtime. We're just going to fix allocate 1,000 materials basically, and that will be at the lowest resolution, which I think is 64 by 64. We'll look into that number, and then we'll have different array layers for different LODs. So one thing is that each layer is also going to have a full MIP chain. All right, so it's going to have a bunch of like, for the way people typically structure it, something like this, isn't it? But for a full MIP chain going down to like 1 by 1 pixel. So this one will be 64 by 64, and then 32 by 32, 16 by 16, 8 by 8, and so on, right? And so there's a 4-MIP chain inside one array layer, and then you have another array layer, right? So this is the lowest resolution texture 2D. There'll be another texture 2D which will start from 128, right? And there'll be another one which has a 4-MIP chain like this, going down all the way to 1 by 1, and then you have a one from 256 and so on until you get to probably 2K or maybe 4K resolution, right? So these materials will be loaded from disk. They'll obviously start from 4K on disk, but depending on how big they are on the screen will determine what LOD is loaded in the material cache. Now in the material cache, we're only going to have like a handful of textures at the highest resolution, at the highest LOD, and there'll be more and more as the LOD decreases, right? As the resolution decreases, so we can have more of those. And the idea is that I want to have a maximum number of unique materials in GPU memory at once. So we're hoping to restrict this kind of per level or per region in the editor, but it's not going to be a hard limit in the. Sorry. Yeah, we're not going to have. It's not going to be explicit though, is what I'm trying to say. It's implicit. So when we load a material that has a certain number of, load a model which has a bunch of materials, we'll go over the material indices, and if the material cache is full, we just won't try and load this model at this time. And that's the sort of errors that we will encounter when we do not respect this restriction here of 1024 materials. And I was thinking that like by limiting it to 1024 materials loaded at once allows us to do some things like, well, we can preload all the lowest resolutions into memory, and it shouldn't use up too much GPU memory, and it means we won't have to keep it shouldn't be too much memory, and it just means we won't have to keep shuffling stuff around. So we can pick like a 64 by 64 resolution, and it means all the we shouldn't start from 1 by 1 because it doesn't make too much sense, right? Otherwise, I have to keep uploading all these small little chunks and loading them from disk all the time. But if we pick like a good base resolution to start from, then we have that loaded into RAM all the time. And then only when stuff becomes higher detail, we can stream it in. Now, it also allows us to, I'm thinking the way we determine the LODs is when we render them, we can get back information when we render it. So there's a compute shader which emits all of the ellipsoids, and we can dispatch another. When we emit the ellipsoids to render, we can also emit the LOD, like the size of it on screen. So you have like an ellipsoid, right? You have the screen. When on the GPU, you have the ellipsoid, and you can get the size of the box on screen, so it means you can get the height. And then we can use that to determine the level of detail for the material. So you just push that to another buffer. And I think by limiting it to 1024, it means we can basically write a reasonably fast compute shader just to sort of atomic max into the local device storage, I think it's called, the LDS memory, the group shared memory of that sort of memory, right? Inside the compute shader. We can just atomic max into that, and then atomic max out to main memory, and then read this back in the future frames. And then the material cache can just simply load the LODs which are requested a frame or two later. And then it'll take like a frame or two later to stream it in. So it might take like it might take about 4 frames or whatever to get it updated, but that's the kind of latency we'll be dealing with. So that'd be interesting. I just hope this is fast enough, basically, is my main concern. Alright, no sugar. Fair play. Fair play. Are you like, what's the reason for the black tea? You like lactose intolerant or something? Okay, so we're going to start off on this material cache. It's another thing from the GPU. So the graphics system. So I don't know why I typed in shader. So, oh, a range allocator. How nice. I don't know how long we're going to keep this BVH system. Right, so this new one is going to be called the material cache. So let's just write out the whole thing. Material cache init. It's going to be some global. It's going to be globally accessible, so I don't have to worry about passing it around because there's only going to be one of these guys. So right, so with the material cache, we're going to want to have essentially a pool of materials. So I think we can get around that by just defining a sort of ID, identifier, and that would just be a graphics material ID. So you'll be able to convert like an asset ID into this sort of material. My one concern is though is like you could probably call that material metadata because it's not really a material. What did we call it on the model? Right, we called it a model, and then we called it a packed model on GPU, didn't we? Right, I see. Excuse me. Right, let's just call it a material. Okay, so I also like coffee, but not as much. Fair enough. I also just like the taste of it. It helps for concentrating. Been drinking it since childhood, but too much is also not good. It also contains caffeine. Yeah. Definitely. I'm quite liking these peppermint teas and these ginger teas because they're good for your gut, which I've been noticing a lot since I've been drinking a bit too much Coke. It's not really been great on my gut, but lost my tea bag now. But yeah, they taste good as well. They're quite refreshing and nice, and yeah, have healthy properties to them as well. So it's pretty nice. Ginger and peppermint, they're good for you. And yeah, and these ones don't have caffeine as well. So this material is going to have it's going to reference some kind of, it's got to have some reference to like a slot inside of it, one of the texture. So I think one of the textures, I think you've got to probably say like, you'll have the LOD. I think we should call it LOD. And then we've got to have like what slice within or layer index within the texture that it's referencing. So that means Yeah, so I think you got to have an LOD thing, maybe. Material. So there's like a texture, and then there's probably some kind of custom allocator in a sense. Uh, well, okay, that's the thing. You have a bunch of textures actually. There's like a material. Maybe you don't need a structure for it, because then you'd have to name stuff. So we'll probably have some kind of like graphics material cache LODs. Maybe we might make this dynamic at some point, just to keep it a constant for now. So you're going to have a bunch of resource IDs. These are going to be all of the different No, we're going to need it in a structure. There's no way about it. So I gotta think of a name for this. There's a material cache. This is like the overall system. You're gonna want to have like a LOD cache, we'll call that. So that's gonna have an array. Well, it's gonna have a resource ID. So this would be for like the albedo. So we'll have all the different ones, right? So we already worked this out. So albedo emissive strength, metalness, roughness, and normal. I don't know if we'll need the height. We might actually need the height for it'll be like screen space shadows or something at some point. Or maybe that's an AO map that we need. I don't know. I gotta figure that one out. But anyway, we'll just so these will all be like texture 2D arrays. Right. And then on top of this, you'd also need a custom allocator of some kind. So we'll need like a different allocator for getting a single slot or something like that, right? So you'd have like this would be the LODs, based on like graphics material LOD. So you have an array of these, and how big these are, how many array layers these have depends on the LOD, right? The higher the resolution, the less we'll have. The lower resolution, the more we'll have. The lowest LOD will have 1024. So if we need some kind of custom allocator here. I was thinking, since we only have at most 1024, we only really would need we could probably get by with a bit set and just traverse the bit set and find the free slot. And then that way these things would be in order. Would be kind of in order. You won't have many holes within the in the array layers. You'll kind of fill the nearest hole. You'll fill the closest slot. Whereas if you did like a linked list, it's whatever's last freed basically. Unless you ordered the linked list. So that's only 16 8-byte integers you need to store that bit set. So that's like 2 cache lines or whatever, isn't it? Because 8 times 8 is 64 bytes, right? So it's 2 cache lines it fits in. It should be quite alright. To just traverse over that at most. Should be ideal. So we could basically store in here U64. You could store the is allocated bit set. So this would be all the slots basically. So these have at most 1024. Each of these is the same resolution and has like at most 1024 array layers. And this allocated bit sets to track those layers, right? And gonna make an array. So that would be 16 you need at most. Which would be yeah. So you could say divided by 64, right? It's a bit crap, to be honest. I can make you read a bit better, to be honest. Maybe we could say it's a bit crap. I don't know. It's a little bit more readable. Anyways, just right. So with this, we can just iterate over all that bit set and find the next allocated slot. So whenever you want to allocate a new material, it's not that bad to do that. And then we'll have less holes and stuff. And then when you want to iterate over all the materials, it's just checking a bit set and doing the least set bit thing, which is pretty cool. So that'll be quite nice. We also need to probably keep track of the number of, so at most you only need 10 bits. So we could probably get away with U16s, I guess. We've got to reshuffle this around. So have like a layers count, layers capacity, basically. How many were allocated? How many? Well, the layers cap is always, well, it's not always 1024. It depends on the LOD. That's good. Oh, a bit strong there, to be honest. All right. So How will we shuffle this around? So really should put these at the top. Keep them in order. This is 32 bits each. So and maybe you should align as a cache line or something. Align as cache lines, that'll round it up and all that. It's alright. Does the job. So that'll be alright. So how many... Yeah, I guess this is okay now in terms of the design there. The material, so you'll sort of like pool allocate these. This is done like a pool allocator, so we need to make ourselves an object pool. So the type will be a graphics material, and then we'll put in a graphics material ID as the second parameter. Now we can just simply declare this sort of object pool here. I use these all over the place. So object, I guess we'll call this the pool. So this, the index into this pool, it's just an array basically with bookkeeping. This will map into the GPU buffer as well, that same index. And that will hold all of the texture and slice index that it's using. Texture and layer index, that's it. So what other information does this need? It's got the LOD. It's got should probably be stored as a floating point, because then you could probably do some gradual decaying or something like that. Yeah. Flawed. I don't know, F-lod. Flawed float, there you go. Cool. Right. What else would you need to keep track of for a material? I don't know what we'll need. Let's go back to that material plan. So merge the GPU. Write an asset path hash to material index. So we need a hash table for that. We've currently not really got a good hash table for just having hashes as keys. We need to sort that out later, but I've got a hash table. I need to declare another hash table. So I'm going to be able to take a hash table, an asset. Have I done this in the past? I think I have. Yeah, I've already got one here. That's good for the mod. So one asset will get you a material. And is it wise to store that in here maybe? Yeah, because when the material goes, it needs to then remove itself from the hash table as well. So I need this is 64 bits, so that'll be a something like that. That's ideal. And what else would you need? What did my docs say? So yeah, we've got to figure out the LOD ranges, isn't it? So like, how many LODs we're going to have determines on the ranges. I think we should support up to 4K textures, right? Obviously, so we'll generate 4K materials in this material editor that we're building. And that should be good enough for a good while. And the lowest LED, the lowest resolution which probably load is LOD dim max, so that'd be 4K, and the min dim would be should we say 64? So let's do a bit of maths, right? So if you're going to have 1024 textures loaded into memory at once, if you were to say so we've got a lot of these different textures, but I guess we'll just take a worst case. So if we take 64 squared, that's 4K, right? But that's only at 1 byte. One question. In Vulkan, do you need to write your own mipmap algorithm as opposed to OpenGL's generic maps? Yeah, you kind of do. But so we ported AMD's single pass downsampler, and we use that. It's actually really good in terms of speed. Like the performance on it was incredible. But it only takes it only does a 2x2 quad. So I guess I can show you off the code that I've done for it. So I've made it a single header for my shader compiler. So you just need to include this header file. Like they've scattered theirs across a few header files, so I just had to combine it into one. But I include this header file and have to declare a bunch of functions. So 3 of them. A load function, a store, and then a reduce function. So reduce just means, hey, take 4 pixels, so 2x2, and output 1 pixel, right? It's a downsample. So I got some functions like reduce min, reduce max, reduce mean. So that just takes the min of all the 4 pixels, this takes the max of all the 4 pixels, and this takes the mean, the average, right? Or you can do like a custom one. And so you define your ways to basically downsample a 2x2 at each MIP level, and then you just include that header file, and then you launch the compute shader, and jobs are good. So this is the thing that I'm talking about, what I ported. And this will do it does a full downsample all the way from your top resolution all the way down to, it does a full MIP chain, right? The only downside with it is that you have to write, is that it's only really designed for square textures at powers of 2. Sorry, it's designed for power of 2 textures. So it can be non-square, it just has to be power of 2. If not, you get a bit of funny behavior sometimes. But it's still possible. It's just for occlusion buffers, it wasn't the behavior I wanted. So I had to make it a power of 2. But it's really good, the speed's great, does it all in a single dispatch, which is incredible. So, highly recommend. It supports up to 4K. If you're going to need to do a downsample, which is kind of a basic 2x2 pixel downsample, it does the job. But for the balloon, we had to do a custom downsample, so I've got to try and write a shader which is inspired by that one, which does more of a wider kernel. Yeah, until then. So let's work out this LOD, the lowest LOD that we want loaded at all times. So let's just say 64 by 64. That's 4K. And so if you got, that's with 1 byte each, right? So how many bytes we got? So albedo is, right, let's work that out. So albedo is how many floats? Well, it's not floats as it is. Right, AAA sRGB. Right, but that needs to be 4 bytes anyway. Yeah, 4 bytes per pixel plus another 4 bytes. Like the only way you can get away with it is if you used a BC1 or something like that, or BC7. But yeah, that won't be for a while. We're not doing that. 4 bytes plus 4 bytes plus 2 bytes for emissive plus another 3 bytes for those three, their metalness, roughness bytes, and plus another. See, that normal can actually be packed down into a 2 byte channels. So it's 15 bytes. Okay. So we take that 4K that we had, that 64 by 64 base resolution. So we timed that by 15. That's for a single material, that's 61K kind of. So we times that by 1024. That is 60. It must be 62 megabytes, right? Or 60, it's about 60 megabytes. We divide by 1024, divide by 1024, 60 megabytes. So 60 megabytes will be loaded in VRAM for the lowest LODs, right? So if we start off at 32 by 32 instead, with 1024 loaded, that will be 4 times less. So that'd be 60 megabytes divided by 4. So it's about 15 megabytes. So that's probably a more reasonable number. Although you're getting like gigabytes these days, isn't it? You get like quite a lot of VRAM. So maybe... No, 32 by 32 is quite reasonable. It all depends on how big the ellipsoids are, isn't it, on screen, basically. Let's do the 32 as our minimum. So it really does depend, though. No, let's do 64. We can always change it. And in the game, which map level is used during rendering is done automatically by GPU based. It depends on the question you're. I'm not sure entirely the question you're asking there, Peri, but so the MIP level can be automatically. When you do like a sample, if you in a pixel shader, if you just call sample, whatever it is in HLSL dot sample, it takes the derivative of a 2 by 2, or maybe. But it basically works out automatically, right? Because it's in a pixel shader. You put the UV in, you put the sampler, you put the whatever, and that will automatically compute the MIP level for you, because it essentially does behind the scenes. Well, it can do this behind the scenes. It takes a 2 by 2 set of pixels, and it essentially looks at the UV values in each of them and works out what is the difference between these UV values at these 2 by 2 sets of pixels, and then it will calculate the MIP level based on that. It's pretty clever. So you can do this yourself, which I'm going to have to do because I'm using compute shaders, and I have to use sample level and pass in my own MIP level in here. So I'll have to somehow work out the derivative in my compute shader when I do my material sampling code. Does that answer your question there, Peri? Or is that something else to do with this thing? Or are you worrying how I'm loading them in? Was that your question? So yeah, we load at minimum 64, 64. So the number of LODs we'll have it's not 8 then, is it? So 4K is like, what, 13 is it? Or it's 12? Yeah, yeah, bit 12. The 13th bit. And then 8 is the 4th bit in. So in terms of the number of LEDs that we need between there, I guess we want like a log 2 min. Run out loud. Log 2 min will be 3 obviously, and then that would be 12. So that'd be the max. Wait, that's 8, isn't it? We meant 64. So that's 6. Gotcha. So now we can work out how many LEDs we have by doing this maths here. Nice. So that is 6 LEDs we'll have. So we just got to work out. All right. Okay, so that'll be good, I reckon. Okay, so what else do we need to do before we, with the data and everything, before we write code? Just go to the material plan. So 1024 max unique materials memory at once. Yep. That seems all okay. 2D arrays. Yeah. Yeah, I think we need to write out the functions now, basically. So we need a way to take in the material, the path hash and get yourself a material ID back out. So you want to be able to say, probably do like a find, we'll call it, not a get, because find is more sort of like I'm searching for it type of thing. I usually like that word better. So we're going to go ahead and pass in probably one of those asset hashes, because that's what the model is going to have. Maybe. Or maybe we'll have some different ID system. Wait, what should these... It might be a hash of the asset. Contents itself. Yeah, I might do that actually. Yeah, we'll change it later on. Let's just get it. Let's get it in. But essentially what I want to do is hash the contents of the material and then use that as the hash rather than the path. Yeah, it just means you got to load all the ones in all the assets in a directory. Okay, we need to write that down. So let's go to that material plan. So what we need to be able to do, I guess we could do as part of this asset thing. Asset files, build functions. So we want to make it such that you need to store these hashes somewhere though. Right, we'll just leave it as this for now. Maybe we could think about you know, I'll think about it off stream. It's not the time for now. I'm a little bit confused, not gonna lie. I think I don't really understand in details how and when MIP levels are used exactly. So far, my understanding was that objects that are far away, for example, will use small textures, yep, with less details after generating MIP. Yep. And how are they selected during the sampling was a mystery. Gotcha. Thank you for finding that. So, right, I guess the first reason is, why do you have MIP maps? Right, well, the problem is like, say if you have like, say if this is your render target, and this is, it's very low resolution render target, and you have a sphere or something, or maybe you have like, let's just say there's a, this is the image you're trying to render, and it's an image of like a person, right? Very bad example. If you was just to take, and this is made up of loads of little pixels like this image in the background. If you was to sample a 2x2 set of pixels, like this is your render target, right? The big grid, and this small grid here is in this background person image. A 2x2 set of pixels, because you're sampling in the center of the pixel for this render target, you're going to get the UVs and then sample this 2x2, and you're not really going to get the area which covers here, right? So if you want to do that effectively, you'd need to sample all of the pixels, right? And then take an average of those basically, in a sense, right? So the way it's done is you generate the MIP levels. So what the MIP levels do is make an average of this person in the background. And you'll essentially have like another grid of low resolution pixels for this image that you're sampling, right? And you'll notice here how it kind of goes, doesn't match up exactly, right, of course, because that's how UVs are like. Now this is the sample position in the center of this render target you're trying to render. And so it's going to do a bilinear interpolation, so for this MIP level. So it's going to give you more of this pixel here, and less of these guys, basically, right? Kind of, because it's a little bit off from the center. It's more of these two, but more of this one, and less of these two over here. And so this, essentially the MIP level is the pre-cache of like all those small resolution things, right? So when it comes to the sampling, is that it calculates so it gets the UV, I guess is there a good example, So essentially when you run a pixel shader, it knows a quad is the smallest unit of computation, right? So these are the 4 pixels that you're rendering in a render target. This has a UV of 0 point something, this comma 0 point something, right? And this one has another 0 point something or whatever, right? And so on. They've all got a UV. It swaps them, does a subtraction, and gets the absolute value, something like that. And it does it sometimes with horizontal and vertical. This is with like the DDX, DDY stuff, if you've seen it in like this DDX, DDY thing. This is one way that it can compute the MIP level. I think there's other ways as well. So it swaps them with the quad, across the X and the Y. And I think it does this F width thing. So it swaps it with the X and Y and takes the subtraction. So the F width is basically doing that, right? Does the X-axis subtraction, Y-axis subtraction, takes the absolute value, adds them together. And then that's the F width value. So what does that give you? Well, it gives you in texture space, right? It's this texture behind us, which has a small resolution like this, right? How many? It gives us essentially in texture space, in UV space, how many pixels or it's in UV space at the moment. But what you need to work out is which MIP level do I need to use to make it such that the pixels are the same size as this sort of like this grid that I'm sampling from in this texture space is the same as this grid is 2x2. So I kind of forget the maths exactly, but it's something like, I could work it out if I spend more time, but that's the basic idea, right? There's like a mid-level calculation that you can look into. There's those resources online. Maybe this is one. Yeah, here you go. Yeah, so you just take the log 2 of so something like this. Number of MIP levels, right? Yeah. Something like this, basically, is a little bit of a, probably help you understand it, but just give it a search. It's something along those lines. And the GPU does it automatically for you if you use sample. But you can do it manually, and you sometimes have to do it manually or cache the manual result for later on, if you don't always have that information available. I think for deferred pipelines, sometimes you have to cache it for later. No worries. Yeah, it is a very much a weird thing. I didn't know until someone told me about it. I was like, what? Does all this magic behind the scenes? It is kind of slightly documented as well in the sample instruction, I think, in HLSL. No, it doesn't say it. It doesn't say derivative. Yeah, I don't know. It doesn't really say. It probably says it somewhere in the spec. Yeah, so you need to be able to find a material, and whenever we with this sort of asset thing, then if it doesn't exist, we need to be able to insert it in there, right? So we need a find, and we probably need a find or insert, which can fail. We probably just need a find or insert. Let's do both, I think. Let's offer both. Right, what else do we need from this material thing? We need the ability to take the uploaded set of data, sorry, the read back set of data, the LOD calculations from the GPU, and feed them back into the material cache. So this will just say, so that happened at the end of the frame, and you'll say, you want to say, so it'll always be like 1024 of them or something like this. And I don't know, what would you call it? It's an array of probably floating point values. Material LODs. So you take the material LODs, you go over all your materials, and basically figure out which ones you want to be streaming in from the disk again and updating, which ones you want to be sort of, which ones you want to be shuffling around basically. You know, do I copy it from this one to the other one and downgrade it, or do I load in the higher MIP into, you know, copy it to the new place and then grab the higher MIP from disk again and stream it to the GPU, basically. So that will be kind of, yeah, process LODs would be it. And that'll be the end of the frame. And then, so if we had like multi-threading and stuff, there'll be a background thread which will probably do a lot of this stuff. All the streaming and that, but we don't have that at the moment, so it'll happen all in here for now. Okay, this seems pretty reasonable place to start. So I guess let's try and get this thing up and running. It's just, I just had a thought though. The lowest level of detail will not need 1024, because if you can have 1024 loaded at most materials, let's work out how each, so if you have 1024 at 64, by 64, you won't have that, you'd have less, right? Because you've got 6. So the max is 4K, and that's at log2 12, right? Because 1 shift of 12 is 4K. So let's say there's one 4K texture that you can have. So there's one 4K texture that you can have in memory. And then there's 2 2K textures you can have in memory. Then there's 4 1K textures you can have in memory. And there's 8 512 by 512 textures, and so on, right? But will that get us the whole way? I don't think it will, right? So if we keep going, you can only do that 6 times, right? So, because I'll progressively get to 16. Yeah, so how many times you can shift this right by 6, isn't it, basically? So 6 divided by 2s you can do to get to 64. So 1 shift left 6 is only what? Up to 64. So we're going to have to probably do powers of 4 at this point. So if we multiply that by 2 into 12, obviously that gets you 496, which is too many. So perhaps what we need is just a hard-coded set of how many textures for each LOD, and we'll just live with that, basically. Because I don't have like four 4K textures. That's just far too many. Maybe. Like you're never gonna have an ellipsoid which is that big, but we'll see. So there are 15 bytes per pixel, right? So we did 4K times 4K. It's 15 bytes per pixel for those PBR textures. So that's already 16 meg just for one byte. Times 15, that's 256 megabytes, right? Now I was going to have like BC textures and compress that down. So that was going to help, but it's about 256 megabytes just to store a 4K texture, which is quite a lot. Or maybe we can support any up to 1K. Yeah, so I guess maybe we can write out the maths here. So if we have one plus 4 plus 16 plus 64, so powers of 4, right? Plus 256 plus 1024. Now that's where it gets a bit too much, right? So that's 1, 2, 3, 4, 5, 6. That already goes over 1024 text materials. So 1 plus 4 plus 16 plus 64 plus 256. That's 341. So we could take that last level, the lowest resolution, and just clamp it. So the final MIP will be left to, so we'll do powers of 4, but the final MIP will be left to what is remaining. So it's 1024 take 341. So 683 low resolution textures. Right. That's something we could do. Or low resolution materials. That's one way we could do it. So yeah, we could do powers of 4 from the highest resolution, then just clamp it for the lowest resolution, such that it makes sense. Yeah, I think that'll be good. Cool. So let's start writing code. Sounds like a plan. Oh, what did I do there? Graphics. Cool, so start with initialization. I think we're in quite a good place to do that because we've thought it out quite a lot. Oh, I didn't write the hash table in here. Hash table. And it's got a hash table of asset path hash, which we might change later for the actual asset hash. And you get out a material ID. So asset path hash to material ID map. Very lovely long descriptive name. So I could just call it a hash. Yeah, this is just called a pool. I could just call it the map. I don't know. Okay. So let's initialize everything correctly. So we're going to need to get the static allocator. Like so. Now I need to initialize our object pool. So this material cache has not been placed inside the global graphics system, so I'm just going to find a place to throw it in there. And the capacity is graphics materials cap. Have we got a thing for that? There we go. Hey there, tangent. Yep. That's a nice summary of it. Have you got any references to that? Just so that Peri Peri can look at the maths and everything for it. I found one briefly, but it wasn't really the best resource. Yeah, it's kind of like secret magic they hide behind the scenes. Well, why is it? Oh, for crying out. Oh, wait. And then you gotta do a dot pool. Right. Okay, so we're gonna get a graphics material cache, and we'll just get a cache pointer because writing this out all the time would just be annoying. So you just make it shorthand basically. So we'll just store that there like that. Good. Okay, so initialize the object pool. Yeah, doing it for 30 years, yeah. Nice. Very cool. So I guess you worked on like... Now, what have you been working on? You must have worked on like PlayStation 1 hardware, right? Maybe? Did you start on the PlayStation 1 then? N64. Wasn't a rock. Nice. I played that game when I was way too young. That's awesome. How much game development has changed, eh? It's cool though. Are you still in the industry then? Or is it you who said you don't work in the industry anymore? Vague memory of someone. So the hash function was a FNV hash. Key compare for hash. Yes, super bad. It doesn't do anything basically. Oh, key hash. Then key. Oh, for crying out loud, where's the key compare? Gotcha. Told myself in the 90s, worked in games for 10 years, web company. Oh, yeah, I remember you saying. Right. I remember your name a bit more now. Then switched to hardware stuff. Cool. What hardware stuff are you doing? So what do you mean by hardware stuff? It'd be quite interesting working at a hardware company. Get to learn about all the ins and outs of how that hardware works. That'd be fun. Maybe get more tools to play with as well. And learn some cool stuff. So the LODs, we've got to go over all the LODs and now initialize all those things. So for every LOD, now the problem with LOD is we have like a min. Crying out loud. Well, it's a small team designed a low-powered AI chip for background AI stuff. For listening to stuff like "Hey Google" and detecting your face in front of your phone camera, right? Did assembly language with a bootloader and a hardware simulator. Sounds pretty cool. Pretty hardcore. It's amazing. So the problem with the LOD is that you've got this sort of like min and max thing. But then like it's a log2 min dim. Yes, so that's not necessarily what the right. Yeah, so we'll call this LOD log2. Or dim log2, I will call it. What is a dim in log2 space? Right, and then this would be called it. Right. That makes a lot more sense for naming wise. So an LOD would just be 0 to 6, basically. LOD's capacity, yeah. Or why is it a LOD's capacity? It's more like just a LOD's. LOD's count, maybe, if you're going to call it like a count thing. So what we need to do is go over get the LOD cache. And this has a bunch of texture arrays for each PBR texture. This is the LOD cache, LODs, LOD. Now we get to initialize all these textures. So it's a graphics, sorry, GPU, texture init, static. Now this is going to be the albedo. Now the problem is this name is kind of... Yeah, I'm going to have to change the texture view a bit to account for some of these things. This is like the material albedo. This is a GPU texture 2D array. The format is currently going to be a 888 sRGB, so we get the auto conversion. And the dimensions will be based on whatever. So we'll be able to basically say, right, to get the dimension from the LOD. So I can make a nice little function for that maybe. Don't know when that's been shared or not, but you take the LOD, you would add, you go graphics, material, LOD dim, log2 min, add the LOD to it, and then you basically one shift left that, and that gets you your dimension, right? So that gets you the dim, and then you can basically just do a 3 dim, dim, dim 1. Right, it's 2D, right? So you don't need 3 of them. And then your MIP levels will be... It's be a full MIP chain. So I think if we did 0, I think it automatically calculates the for. Oh no, it doesn't, does it? MIPS count GPU MIPS from max from dims. Great, so I can pass in a dims equals dim1 dims.xy. Okay, and then this other one is the array layers. So it's MIPS count. Now the array layers is that other little bit of. So I think we will kind of want to do a reverse here because we. Yeah, let's do them in reverse. Awesome. Amazing. Yeah, all the resources on LearnOpenGL are really good. It's amazing that they're there. Hmm. Oh, like compile time's a problem. But yeah, I guess like I don't know. I guess it's just a preference thing if you like web technology, but yeah, web tech's just a bit. Yeah. Yeah, OpenGL is a bit of a weird API. It's just weird in general, right? It doesn't really. But yeah, there is the SDL3 library, SDL3 GPU. So whenever you feel like doing more of the newer sort of APIs, there's SDL3 GPU, and it's basically an abstraction on top of Vulkan and stuff. It's pretty alright. It's good for indie developers, I think. Doesn't support all the new features though, but it's basically good for everyone. Yeah, it's pretty nice. So I would recommend that one over WebGPU, to be honest. WebGPU's, yeah, it's mostly good WebGPU, but STL3 is a little bit more simpler. But by then I'd already learnt Vulkan, and I already was like, but I could do it this way, so I don't really use those things, you know. So the array layers, I need to calculate those. Now I need to do a reverse loop. So if we'll say index, and then we'll do a LOD equal the count take index take 1, and that'll do a reverse loop, right? Now, since we're doing the reverse loop, we can accumulate the number of layers, right? So you accumulate the number of layers. Yes. Array layers equal 1. Now you need to be doing shift left by 2 because you need powers of 4, right? So you put in your array layers and you say array layers shift left equal 2. Right, so it'd be like 1 shift left 2 before, and shift left another 2, 16, 64, 256, and then 1024. Now by then you've gone over, because we only support up to 1024 materials. So when you get to it at this point, because you're on the last LOD. Oh, we need to build up the accumulation as well. I think that's the idea. We need to build up the accumulated. So then that will be like and then I think what we need to do is clamp. So you go if accumulated layers is greater than graphics material. I could just say if it's the last one, right? Just make it accumulated layers take. Yeah, let's just say if it's the last one. It's easier to understand. Graphics materials, LEDs count. Then the number of array layers is simply, it is simply just accumulated array layers take 1024. So that the accumulated layers was 34. You'd have done added 1024, and so you're just taking the 1024 to get. No. It's not what you wanted. You wanted to do 1024 take the accumulated. Oh. Yeah, what's a good way of doing it? You want to remove the... Alright, don't add the 1024 because that's where it gets added. And then just do 1024. Take that. So I guess if we just put a comment here saying like at most we want materials cap. We only need to have textures loaded at worth of materials loaded at one time. The lowest level of detail only needs, so essentially we're doing powers of 4. We're starting from the highest LOD with one layer, array layer, and oh, they fixed that thing in Helix. You press enter and it puts the comment on the next line. Win. Like a bit of a basic feature, but they put it in there, which is great. Array layer. Run it one array layer and go down to the next. Go down an LOD and move the array layer count to the next power of 4. As we repeat this, the lowest LOD will go over 1024. The lowest LOD as we repeat this accumulatively, is that you spell accumulatively? Or is it cumulatively, isn't it? Because increasing or growing by an accumulation or successive additions. So you have accumulate. Accumulatively. I guess that's the word I'm looking for. English. Accumulatively. Well, I only need we'll end up with far more textures. What's the best way of saying this? The lowest LED the number of aka one material at a I'm using the Helix editor. So it's inspired by Vim, but it's like a modern take. You know, it's written in Rust. So it's where all the cool kids are at. But yeah, I like it because it's just got a simple config text file. It's not, you know, config this like big old Vim script or Lua thing for a text editor just to get going, you know. Have you used Rust? Yeah, I used it for 4 years before it was cool. I used it back at 0.83 or something like that, all the way to 1.34. And then I was like, all this borrow checker stuff gets in the way of programming, so I kind of went back to the unsafe way. But I think it's a great way to bring people down from web tech into low level stuff if you don't get all into cargo and download a million packages just to do the basic thing. If you really get in there and learn low level stuff, it's a great way to step down, I think. Maybe there's other languages which are better for it, but Rust ain't bad. It's got a hand-holdy feature with the borrow checker, which is kind of alright for new people. Helps people think about things in a certain way. But it's probably not a good idea to build big software in. One material the highest LOD. As we repeat this cumulatively, the number of materials left of materials for the final the lowest LOD needs to only needs to use the remaining number of materials. There you go. So I guess so you'd always get one. So I guess the problem with that, doing it that way, Maybe the problem with doing it that way is that you can't just load them all in it. You know, say if they're already small, why do you need to load in the bigger ones, right? But the memory's already pre-allocated, but it's just the streaming cost would be less, right? Yeah, you know what, we'll actually make it such that instead we'll do this. Array, so you'll add it, and then you'll just do like a min operation or something like this. You do like a core min graphics material cap. Yeah, that's it. Oh, no, 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 no. You don't need an accumulated anymore, isn't it? So, whoopsie, my mistake. This is what I meant to do. Core min graphics materials cap. That's it. Okay, that's much better. That'll do it. So, right, that's just albedo. So we need to do this for all of them. So emissive the emissive sort of base color, the emissive strength, that is only needs to be a unorm. Oh, no, 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 not a unorm. It's a U6, it's a 16 float, because it brings up into HDR, doesn't it? Multiplies the base color. Then we need a metalness, roughness, and height. And then a normal map. So those are 8 unorms, these guys. They're linear textures. And that is also an 8 unorm. And then this final one. Now this could probably be a metalness and roughness map, since you're going to need them both at the same time anyway. Metalness, roughness map into a single texture. That will just help with access patterns, basically. You just load 2 channels. Because you need the data when you look at the same time anyway. High map, B norm. And then this would be an A8 unorm as well, because you can reconstruct the Z channel from the other two. So that's just a compression technique. Cool. So I think that's the initialization code for this caching system. Now we just have to figure out how do we, I just have to write the rest of these guys here. Just go back to the, there's the layer allocated bit set. That'll just be a mem set. You zero the whole array, so it's it's just lod cache is allocated bit set. And then we need to also do like a layer. Wait, I didn't even store this. What a bugger. So LED cache. So the metalness roughness, we're going to change that in the, so there's a metalness roughness texture. The only problem storing is meltness, roughness. You have in the texture view. You have to look at the single channel, but we've got support for that anyway, so it's not the end of the world. Cool. Okay. Hey there, the Shadow. Not doing bad, man. How are you doing? I've been quite tired lately, to be honest, but I'm doing good. It's been very busy and not getting the best of sleep, but yeah, things are going alright. You know, with last stream we added shader hotcode reloading and support for multiple shader packs, shader binaries, so we can procedurally generate materials with shaders. This is the plan. So I built a big old plan to. We're currently getting support in for the renderer where we can build. Where we can sample materials from textures, like PBR textures, rather than just passing in the raw values for the whole ellipsoid, because we render with ellipsoids. So we'll be able to get like some nice detail, micro detail on our primitives that we're rendering, which would be pretty sweet. So I'm just building the renderer side so we can sample for some textures. And then after that, we'll be building a custom editor where we can essentially build some kind of like, if I was just to give you a basic idea of what it is, if you're familiar with like Substance Designer, you know, people use this to make materials and stuff. Well, you know, I'm essentially building this, but without the node graph editor. So it's just all, you just write shader code. I've got a texture viewer anyway, I could just use that. And we'll have ellipsoids and things that you can view, and we'll be able to write our own little materials. We won't be doing anything like this though with the parallax occlusion mapping, but yeah, it's going to be cool. It's going to be all in the game. Make our own little custom materials, and yeah, this is what we're working on for the next few months. But yeah, how's things going with you, The Shadow? Welcome to the stream. So we also need to set the LOD cache layers count to 0. It's probably already set anyway, but let's just set it. And the number of layers, the capacity for these is just array layers. Observe, good. There we go. So that's all the initialization code done. The next step is to get this cache find or insert, and the process lots code. So these are like when you get a model in, right? It's got a list of materials. We need to search it up and make sure it's in here. So that's what the find or insert will do. The find is there because we might just need to do a find. But we'll see. So I'm just going to take a quick break, but in the meantime, feel free to ask questions. When I come back, I'll answer them. Any questions about the project, feel free to ask away. And yeah, I'll be back very soon. Alright, welcome back everybody. So, the find one is very easy. It is just gonna use the hash table find function. And it's gonna find for the material one. That's the path hash material ID. And we just need to go into the cache, the material cache structure, which is just kind of globally stored, as you do. Look in the map. The key that we pass in is the asset hash, and the entry size we don't need. Right, that's it. And it gets you back a pointer. So the pointer can be null. We're never going to allow you to change it. So we'll call the ID pointer. And we'll just basically return if ID pointer, then return deref ID pointer. If not, return graphics material ID, core ID null, graphics material ID. That'll do it. So yeah, the user can check if it doesn't exist, and if not, they will actually get the proper result. Cool, the next thing to do for the find or insert is to kind of do a bit of a similar thing. We'll use the find or insert function, and that gets you back an isNew boolean. Super nice. Which will help us know whether or not this existed or not beforehand. So what we want to know is, if it is new, then we need to actually allocate ourselves a new slot for this material. Now we don't know it's LOD actually, so I think what we might do is allocate in the I might make an LOD cache function to allocate us a new slot, maybe. So we're going to make a new material, so I'll just do a oh, you want the hash table to be bigger than materials cap, because if not, it will be slow. So if we multiply it by 4 or something, maybe 16 or maybe 8, I don't know. Maybe it's a bit much. Let's make it faster. Okay, so that'll mean then we need to use get a graphics material back from a object pool allocate. So we'll pass in the address of cache pool. So pool allocate, and it will store all the ID into the hash table. And then at the end we can just deref the ID here. Although, can this be full? That is the question. So it can be full. It's kind of the problem with it. Well, we know if it's full based on how many materials that we try and insert. So what we would need in the material cache is just another little boolean in here. Not boolean, sorry, I mean like a materials count. Just a little counter, right? Now, every time we do an insert, this number has to go up by 1. Now the problem is that you can actually end up in a situation where you Yeah, you've actually got. You'd actually end up inserting when you've already filled it up, so you need to be able to remove. So if that is equal to, or greater than or equal to, just to be safe. The maximum number of materials, we'll simply just do a remove. And then return. Now that is going to do another lookup. I could write a better hash table where it gives you like a way to remove it based on the pointer or something, but I got to improve the API anyway, so I can solve that problem later. So we're going to return the null ID at this point. Now the next thing we need to do is yeah, it's got to have ways to unload as well. That's one we didn't do, right? We want to have a way to material cache remove, right? Or right, I think they might need to be reference counted, because every time you find one, it really should. Yeah, so we should say. So decrement reference, or what's the ways you typically say it? So you say reference. When you have like a reference counter, what do you typically say? Let's just say that decrement reference count. But there might be that's kind of the thing we'll be doing internally, but yeah. Something I've got to think about. So yeah, when we do this find, we should actually say, right, if you have this ID pointer, let's go ahead and get the material for it. And then increment material ref count plus equal 1. Yeah. And so when we find or insert when we find yeah, we need to do a get and then up the ref count as well. And then that will be up the ref count here. So this needs a ref count field. We could probably reduce these to 16s, to be honest, and that will pack a bit, because there's 64 bits, and there'll be another 64 bits there. Just less wasted space. So when you find or insert, you get the material. If it's new, if we go over the number of materials, Then just remove this one and return because it's full up. Then up the number of materials, allocate a new material. This is going to be zeroed memory. So the LOD is going to be zeroed. The asset hash needs to be put in there. The layer index, we need to allocate that. The ref count will be sorted out later. So let's sort out the layer. Let's allocate a new layer. So I need to make another function, I think. We'll call this the asset cache or LOD cache. And we're going to allocate ourselves a layer. Allocate layer. Or just say alloc. Right? And you're trying to just say, give me the next free layer index available in that texture, right? And then we probably want to do a dealloc as well, where you're saying, right, free that layer index, right? Yeah, free that layer index in the allocated bit set, basically. Yeah. There might need to be some more functions, but we'll see. For now, these are the guys that we need for the LOD cache. Alright, so come back and do this in just a second. So what we'd like to do is use that function, the alloc, and say, right, material layer index equals this. And this should never fail. There should always be room, because there's always 1024 on the LOD cache. Oh, wait. Cache LODs 0. Boom. Very nice. So what is next? So that will up the ref count and then return out. It's in the map, it's in the pool, and it's got a slot in the texture cache. Sorry, the texture to the arrays, basically, right? Now, the issue is we now need to somehow let the system know that this material needs to be loaded in, right? It's in a sort of unloaded state. So that's something we need to think about when we maybe process the LODs or something like this, is we also need to be able to know, like, you know, what sort of state they're in and load them in and stuff like this, you know? So that's another thing. So I guess let's do the allocation code. No, let's just deref code quick. So the deref code needs to do a find. It then needs to say if it exists. I don't know why it's... Yes, just as a find. If it doesn't exist, just return early. And now this is where we take the material and we go, right, take away 1 from the ref count. Now if the ref count is greater than 1, then just return at this point, right? Now the final thing is we say, well, this is when it's completely gone. So all the references have been given up. So at this point, you could probably say that it's safe to, that the material's been on, there's not, it's, this would happen when the model is maybe not in, all the models have been unloaded. So they remove their reference count. And yeah, I guess let's just do it this way. We can always change it later. So remove it from the hash table. Remove it from the pool as well. And remove it from the material cache, material LOD cache, deallocate. So it's cache LODs material LOD. Its LOD is float. We could probably just convert it to an int and we'll do a clamp. Sorry, a floor basically. And then the layer they want to deallocate is material layer. Return that back to the LOD cache. Nice. That's really good. So that'll be the dereferencing. Dereferencing the decrementing the reference count. So maybe we could say remove reference. So every time you find or find or insert will increase the reference. And then this will decrease it. I've got to be careful. Well, maybe the find or insert should increase the reference only. The find should never. Or maybe the increased reference should be manual. Ref inc. So if you have 0 references and you increment it, well, so it only gets cleaned up when you decrement it back to 0. So when you find or insert, you want it to increment automatically, don't you? Well, you might not. Yeah, okay, let's just do it manually. It's a bit easier that way. So this is decrement. So when you decrement, you've got to do another find. Then get decrement. Right, that'll do it. Then this one, you've got to do a find. Sorry, a get on the with a material ID, that's it. And then increment the reference count. Yeah, that'll be good enough, I think. Right, you need to remove it from the hash table. Cool. Right, so let's write those functions that will allocate those LED cache slots. So essentially inside this LED cache, we've got a bunch of different PBR textures, and they have this many array layers at most. So this is the number of array layers allocated, and we're going to try and allocate them next to each other as much as possible. So we'll have this bit set, which will have a bit for every layer that's allocated. So to allocate, we'll just scan over the whole. We'll scan over the whole array, and so what do I have? So the bit set is set, right? We probably want to get the next set bit or something like that, isn't it? So bit set is set, so you check an actual bit. You can set remove least set bit. This one's handy as well. So to get the least set bit, oh, I've already got functions for that. Right, that's for iterating, isn't it? Right, so to iterate over a bit set effectively, you want to be doing like a while loop. So you for loop over all the bits in the bit set, and then you take the word out and do a while loop. Yeah. So we'll go over all the bits set, all the words, word index, lot cache. So it will take the capacity. This will give us the number of words that we actually need to look over. So the words cap is this number of layers divided by the number of bits in a U64. And then we can use the words capacity, extract out the word, so that would be lot cache is layer allocated bit set, put in the word index, and pull out the the word. Now we can process the word while the word has bits. Now this is where the fun begins. To go to the, you need to use basically, so you need to get your bit index. That'll be the bit, least significant bit that's set in a U64. So pass in word. And then at the end we need to say, right, bit remove least significant bit, and we pass in the word. And that removes the least significant bit that we've just checked over. So that gives us sort of a relative index within the word. So we need to figure out what is the word base index. So there's a base index, and that is word index multiplied by the number of bits in a U64. And with this all in all, you can compute the actual layer index. Which will be base index plus rel index. And now from here, you can just check. Yeah, so this gives you a a way to iterate over every bit which is set, right? So when you allocate, you're looking for the bit which is not set. So in order to do that, you need to flip the word bit. You need to invert the word bits there. Now, so you only really need an if statement here. And then you need to make sure you remove you can then toggle the bit, or you can end it out. Easier with just a toggle, to be honest. Well, and out the not of one shift left rel index. There's your layer index, and you should just be able to return layer index. Now, we might as well return some kind of invalid value, just in case. It should never fail. So again, let's double check that. So we do get the number of layers in this LOD cache. Do I run up by 64? That gives us a number of words that we need. Number of 64 bit words we need in the bit set. Go over all those words in the bit set for the number of layers. Pick up 64 of them and not them, because it is allocated, but what we want to look for is deallocated. So we not invert them the other way around. We calculate the base index for the layer by multiplying it by the word index by 64. And then we say if it has any bits set, calculate the relative. Wait, you're trying to allocate, so we need to OR. It's the other way around, isn't it? Get the relative index by getting the least significant bit that's set. Calculate the layer index. Save this allocated now and return the allocation. Done. So the deallocate. So the deallocate is going to simply index into the bit set with a bit of magic. So in this case here, we're just going to take the layer index, mod it. Now we could probably put a bit of safety code to say, hey, if the layer index is greater than the greater than the LOD cache Yeah, this is where I typically put asserts in, but yeah, should probably have like logs as well, to be honest. Like a way to log it out and keep it running where possible. But maybe we'll keep it with asserts for now. We can go sort out all of our asserts later on. So layer index must be less than the. Well, that's just an out of bounds array access basically. And that's just as safe as rest. And the next thing we need to check is that the layers bit set is not already allocated basically. So you'd work out that sort of like, so it's layer index divided by 64 and then you mod 64, right? You know, that will compile down to some ands and shifts and stuff. So it'll be faster than doing those two things, but that's all right. So this will be, you want to make sure, so you and it, you want to make sure that bit is set because it is allocated bit set. So we're going to say LOD cache cannot deallocate LOD cache layer that is not allocated. Oh, excuse me. So that's a nice little assert there. We should probably have a way again to log that instead of crashing, but I've not got that system set up yet. So the next thing here is to actually make that change, right? We just want to and out that bit, so we have to make sure we not it. And jobs are good. There we go. So that's the implementation of those two functions there. That will allocate and deallocate individual layers within inside a texture array. So that seems like the material cache system is mostly done in terms of allocating slots and stuff. It's just this process IDs, right? We need a way now to be able to load in a texture from disk and put it into GPU memory. And this is what the process LOD should do. It takes the LEDs that they got from the GPU, because the GPU tried to render these ellipsoids, and it's like, well, it wants the material at this level of detail, and the CPU will get it a couple of frames later, and then it can stream in the assets it needs. So yeah, I guess we'll save this for next stream then. So let's go over the plan quickly again. So we've got to write that code where we stream in all the textures and stuff. So we'll just have a simple test texture. I think we'll have like we'll have a color texture. The test color texture will have a bunch of grayscale textures for the roughness and metalness. And we'll also have, yeah, I think that's it, just some test ones just to load in for now. So we can, yeah, it has to do the MIP chain though. That's fine. We can do that. So we'll make those next stream as well. That shouldn't be too bad. And then after we've got the new LODs, we've got that system in place. Then I guess we can test it and make sure it works, right? Make sure the code compiles and it runs. Then we can write this other part of this rendering changes, which is, so there should be 2 more streams left. I'm hoping it's 2 more, but it might be a third, might be a 4th one. So we'll need to go over the materials when they load and get the material the materials of the model when we load a model, and only load the model if we can get all of the material indices from the material cache. And then we need to basically upload these to the GPU. And then we need to be able to, we'll skip the LOD feedback stuff, we'll do that last. We'll need to go over all the models instances and only use them if their model exists. And then we need to do the ray, every time we do one of those ray trace shaders that use the materials, we need to turn that into a UV, calculate the MIP level, and then sample the textures. Right. Yeah, so I think looking into it, I was going to use the octahedral format. So maybe we'll generate some basic textures next stream, save those out to disk, and then, so we'll quickly generate some in a basic shader then. Hey, Peri Peri. Interesting, I'm not sure what thing the bot picked up on. But yeah, have a good night, man. Good to see you. Ah, yeah, so that's basically it. Well, I think we'll generate some textures next stream with the octahedral so we can see it work. Yeah, that'd be a good idea. That'd be cool. So we'll start with that next stream and we'll get in this sort of material loading code after we've generated the textures and saved them out to disk. That'd be cool. Pretty fun. Right, let's find someone to raid in the meantime. So I'll next be on Sunday. I might start a little bit later than normal, so I might start like, you take the stream 2.5 hours ago. It's that time on Sunday, and the same time again on like Tuesday and Thursday next week. We'll be working more on this material system to make stuff look awesome. Right, in the meantime, guys, feel free to check out the Discord and the links in the channel or in the About section. Thank you so much for all the supporters of the stream. Appreciate you guys. And yeah, I'll see you all in a future one. Right, bye-bye.